When you push an architecture past its structural limits, the foundation inevitably fractures long before the interface freezes. The modern developer's choice is no longer a binary one. The historical boundaries between relational and non-relational databases have blurred as tools on both sides adopt each other's features. Since traditional SQL databases can now store and query unstructured JSON, many teams question if the operational overhead of NoSQL is still a requirement. To find the breaking point, we need to look at a high concurrency environment. We're architecting the backend for a real-time collaborative text editor, similar to Google Docs. The load constraint for this specific system is 100 million active users. At that scale, the decision tree changes. We have to identify the exact moment where the safety of a relational schema becomes a system-breaking bottleneck. This quadrant chart maps our choices. The horizontal axis measures relational complexity, while the vertical axis tracks the demands of concurrency and write scale. Standard SQL databases occupy the bottom right. They provide deep relational depth, but their internal overhead limits their performance as write volume climbs toward the top of the chart. NoSQL sits in the top left, designed for high-velocity writes and horizontal expansion. However, most modern applications live in that ambiguous middle zone, where the trade-offs aren't as clear. Picking the wrong architecture at this volume leads to a total system collapse under peak traffic, or a cloud bill that scales faster than your revenue. SQL is built to enforce strict schemas and execute complex joins across multiple tables. This structure guarantees ACID compliance, ensuring that every transaction is processed reliably and that the database never enters a state of partial or corrupted information. This comparison table highlights the specific trade-offs we have to navigate when building for high-traffic collaboration. SQL scores highly for complex relational queries and maintaining a rigid, reliable data structure. However, that same rigidity makes SQL poorly suited for write-heavy loads, where the state of the data is changing every millisecond. If 50 users attempt to edit a single paragraph simultaneously, SQL's row-level locks force those edits into a sequential queue. Each user has to wait for the previous transaction to finish before their keystroke can be registered. Because of these locks, horizontal scaling becomes incredibly expensive. Adding more database servers requires constant, intensive synchronization to ensure every node knows which rows are currently locked. Real-time collaboration at scale requires us to trade absolute relational integrity for raw, non-blocking throughput. We can begin by isolating the document metadata, things like titles, permissions, and creation dates, into its own microservice. Metadata typically exists as isolated records. A document's title and its owner's ID are unstructured data points that don't inherently require a multi-table join for every lookup. By structuring our metadata as independent entities, we can forego complex relational joins. This allows us to prioritize the rapid document lookups required to serve millions of concurrent requests. On our comparison table, NoSQL excels here. Its flexible data structure is designed to handle these kinds of isolated records. This choice allows for frictionless horizontal scaling. We can distribute millions of documents across an array of servers without the bottleneck of a central relational coordinator. The trade-off is that you cannot natively run complex queries across disparate documents. You are limited to simple key-value lookups to retrieve your metadata. In the context of document metadata, the ability to scale horizontally and maintain low latency is more valuable than the ability to run multi-table joins. The most demanding part of the system is the actual editing service, which has to process every character a user types. Each keystroke is an operation that must be captured, transformed to resolve conflicts, and broadcast back to every other user on the document. To survive thousands of these writes every second, we need a NoSQL database like Cassandra, which is specifically optimized for high-velocity write throughput. This architecture relies on eventual consistency. Users might see minor, temporary desyncs as the system merges edits, but they avoid the lag associated with strict relational locking. However, NoSQL databases charge heavily based on the size of the data and the volume of requests. Storing high-resolution images or complete document histories directly in the database can quickly lead to unsustainable cloud costs. We mitigate this financial risk with a blob strategy. As shown in this flow map, small text edits go to the NoSQL database, while heavy assets like images bypass it and route directly into S3 blob storage. The database stays lightweight because it only stores a simple reference link pointing to the heavy file in storage. This approach shifts the burden from the database to the application layer. The front-end client must now manually stitch together the text from the database and the assets from S3 to display the document. Offloading these heavy payloads is essential to keeping the database responsive while keeping the project within budget. Large-scale architectures rarely rely on a single database type. Instead, they use polyglot persistence, deploying different databases for different microservices based on their specific needs. We can map these decisions using a simple framework. For every new data service, we evaluate the requirements of the workload. If the service requires strict ACID compliance and relational integrity, the decision tree points directly to SQL. This remains the standard for financial ledgers, inventory systems, or any service where the accuracy of the record is the primary constraint. If the service faces a highly concurrent, write-heavy workload, we move toward NoSQL. This path is necessary for real-time collaboration, activity streams, and metadata scaffolding, where latency and availability take priority over strong consistency. Scaling to 100 million users requires mastering exactly when to trade relational safety for throughput and when to move heavy payloads into cheaper storage tiers.